All right. I'm going to be talking about Clumpy galaxies and the DYNAMO sample. The DYNAMO sample is a set of galaxies at redshift zero point 0.1 that are extremely similar in properties to redshifts 1 to 2 galaxies. And we're going to be most interested in using them as sort of laboratories where we can study the clump evolution and talk eventually about what we think that might be adding to bulge formation. So we've had this problem for many, many years that we've known that clumps exist in galaxies. These are very high densities of star formation and young stars that make up an individual clump will be something like 10 to 20% of the light of a galaxy at redshift 2. But studying their individual properties is exceptionally challenging just because the galaxies are so far away, even with HST. The spatial resolution on them is not great. The sensitivity is not great. These things lead to systematics, which means that studying their physical properties are hard. Dynamo galaxies are found at redshift of 0.1. They give you an increase in brightness on the sky of a factor of about 30 and a spatial resolution that's about 5 times better. And they do this without the systematic effects that you get from lens galaxies due to your lensing model. And so what I'm going to do is tell you why we think they are similar and then use them as the sort of test case where we can study the details of what happens to clumps and how they might be adding to bulges. So on the left, you see the diagram of star formation rate versus stellar mass for the entire galaxies. The gray represents the entire DYNAMO sample. Now, the entire DYNAMO sample is about 100 galaxies, but we have since spent several years doing follow-up studies where we sort of narrowed that sample down to really just a handful of about 10 galaxies that essentially pass all our tests for being similar to a redshift 1 to 2 galaxy. Here I'm showing you kinematics. So there is this very well-known property of redshift 2 galaxies that they are high velocity dispersion rotating disks, or turbulent disks as they are called. And here I'm showing you CAC-adaptive optics observations of a couple DYNAMO galaxies. There's about 5 or 6 more that we have this on. And where on the left, I'm showing you velocity dispersion, the middle is rotation. And the mid-tone orange in the velocity dispersion maps is about 80 kilometers per second. And what this is saying is that they're high velocity dispersion systems. A typical local spiral is something like 10 kilometers per second. So it's much higher velocity dispersion than you see in a spiral. It is not located at the center. It is not due to beam smearing. And that these are in systems that are rotating. They're not in systems that are sort of advanced stage mergers or anything like that. And you can see on the right, the surface brightness profiles of the galaxies are exponential, much like you would expect out of a disk. Now, I think maybe one of the most fundamental observations of high redshift galaxies and something that may be driving all of the other properties is their gas fraction. They are very gas rich. We've had several studies studying the gas fractions of DYNAMO galaxies. The left shows, just sort of illustrates the similarity of DYNAMO galaxies to high redshift galaxies. The top bin is for the Fibs galaxy, so the red sort of histogram is the Fibs galaxies, and the bottom is the local universe cold gas sample. The gray is where we see DYNAMO galaxies. Generally, we find their gas fractions to be about 20% upwards to 50%, so I think the highest is around 70%. So this is in the range of redshift 2 galaxies. And on the right panel is another property that's very important, and that is the star formation depletion time. So this is the gas mass divided by the star formation rate for the galaxy. DYNAMO galaxies that have high velocity dispersion, which is what I'm plotting it against there, are the ones that have the low gas depletion times, indicating that when the gas is turbulent and acting the way we think a redshift 1 galaxy is doing, so is the star formation. It is making stars at rates similar to a high redshift galaxy, which are depletion times of something like a half a gig year rather than 2 gig years, which is what we get for the local universe. And then finally, of course, if I was going to give a talk about clumps, I should motivate that the clumps we see in DYNAMO galaxies are quite like what we see at high redshift. So here I'm showing in the middle panel are HST images of our DYNAMO galaxies in H alpha. And what I've done on the left is I've taken those and blurred them to the resolution they would have at redshift 2. And you can see that they look, basically, with your eyes, they look like these images that were returned from Forster Scriber and Reinhard Genzel from the SENS programs to show these big giant clumps. And when we quantifiably measure the H alpha luminosity and the diameter, that's what I'm showing you on the right. This is from the same program. The red points are the DYNAMO galaxies at full resolution. We see that their sizes and their H alpha luminosities of individual clumps are the same as the sizes and luminosities of clumps in lens galaxies. Those are the dark blue. But when we take those blurred maps and we remeasure the sizes and luminosities, they basically are the same as the unlensed galaxies. And so what this is telling us is that if you look at a DYNAMO galaxy with the same resolution and sensitivity as you do a redshift 1 galaxy, they have basically the same properties of down to the clump scale. We have a number of things, and this is not all. We also looked at a lot of things like the dust temperature. We have a number of properties where we have narrowed down to have a sample of about 10 DYNAMO galaxies that are really closely matched to redshift 1. Both their kinematics, their gas properties, as well as the clumpy morphology of the star formation. And so now we want to use these galaxies to basically do hypothesis testing. That's kind of how we can use DYNAMO galaxies. And one thing that's been a long-standing open question that has been very difficult to answer with observations at high redshift galaxies directly is, do the clumps live for a long time or do they dissipate quickly? If they live for a long time, this little cartoon diagram, that's the sort of scenario on the right, then basically they will rotate around the galaxy, and dynamical friction will eventually cause them to find the center of the disk, and they will add up and add mass to the bulge. And if you do that for 10 or 15 clumps in a galaxy, you can add a significant amount of mass to the bulge. However, if they sort of blow themselves up, they dissipate rather quickly, then they will never make it to the center of the galaxy. They'll become something like a thick disk star. The difference between whether they make it a long time or rather they are short-lived has to do, basically, it comes down to your feedback model. Stronger feedback models, for example, what's in the Nihao simulation, also what's in the FIRE simulation, tend to destroy clumps very quickly. Ones that rely more on supernova rather than radiation pressure allow clumps to survive, and they reaccrete gas and they keep themselves alive, and they don't just continue to go. They age as they go through the galaxy. They grow mass as they go through the galaxy. And so there are straightforward predictions for the mass evolution of clumps in this long-lived versus short-lived scenario. This is very challenging to test at high redshift for multiple reasons. With DYNAMO galaxies, we don't just get an increase in resolution. We also get other systematic effects, and the left is showing one of those. We get access to near-infrared light. In local universe galaxies, it's not just the gold standard, it's really just required to have near-infrared light to get a mass-to-light ratio that you find trustworthy. But anything redward of, say, 600 nanometers, it's really difficult to measure in high redshift galaxies. JWST will, of course, change this, but for now, we haven't had access to that. But with DYNAMO galaxies, we get K-band, J-band data quite easily with either HST or adaptive optics. And this really allows us to decrease the uncertainties on our mass-to-light ratio. Another thing is that sort of the way that resolution works is it sort of clusters clumps together and artificially makes them look like a super large clump in high redshift galaxies. And what this does is it makes you lose access to the low mass clumps. And the simulations, that's the plot I'm showing you on the right-hand side. This is a result from the Mandelker simulations. What they argue is that it is those low mass clumps which tell the difference between the two different models, because if a clump is very large, even with the strong feedback, it's able to overcome that strong feedback. But it's the low mass clumps that get destroyed that never grow into the big, large clumps. And so we have access to that with DYNAMO. The first thing I wanted to do with the DYNAMO sample when looking at the stellar mass of clumps was just to see, are there old clumps? Do clumps exist in old stars? And we can do that with Keck adaptive optics. We can get K-band images of DYNAMO clumps, and this work was done by Heidi White. It came out last year. And the little insert images on the slide here show you that with your eyes, yes, you can see clumps are existing there in K-band light. And so that's really a nice confirmation that clumps of stars do exist. And the second thing is to look at the masses. And Heidi did that using some simple stellar population models. And you have the stellar mass versus their position in the galaxy. And you see that there is a range of masses as expected in the low mass, in the long-lived scenario. You have a lot of low mass clumps, and then the ones that are in the center are the high mass clumps. We followed this up with an HST program that came out this year. And this was done by Liu Ambachu, my student here at Swinburne. And what you're looking at in the middle is, again, the clump mass versus the position in the galaxy. And the small, large number of points represents different models from the Mandelker simulation. So the gray points in the top figure is a scenario for short-lived clumps. So remember, what happens in short-lived clumps is that the clump doesn't have time. It doesn't have time to orbit through the galaxy and decay. It doesn't grow as it does this. And so what you end up with is a distribution of clumps that are located at large radius in the galaxy and are fairly small. They don't get really huge. Only a few of them get big. And so that is not like what we observe in the dynamo galaxies. Those are the red diamonds, or the dynamo clumps. If we look at the bottom, we see long-lived clumps, and those are the blue points. And in that situation, the clumps are able to travel through the galaxies, so you see more at small radius, and the ones that are at small radius tend to be larger in mass. That is what we observe. So again, we're finding things that are consistent with a long-lived clump scenario. We can also look at what's going on inside the clumps, and this is one of my favorite projects because it's something that you can really only do with dynamo galaxies. This shows two color diagrams, and you can separate out the way that what is sort of reddening the light in a clump based on how the track that they follow in this diagram. So if you find that the age gradient is moving vertically, that if the stellar population gradient is moving vertically, then that is an age gradient. If it's moving horizontally, then that's an extinction gradient. And there was an argument that maybe clumps, they're short-lived, and the only reason we see them is just that there's holes in extinction. If that's the case, then you should see horizontal gradients. So this is something we could check with Dynamo. And the red show, the right-hand panel shows where we've tried to test this on a sample of galaxies, on a sample of clumps from a single galaxy. And you can see they're moving vertically. They're basically tracking the age gradient. And this work was done by Laura Linkage. It came out last year. And what we found is that the vast majority of clumps in dynamo galaxies track age gradients, not extinction gradients. And here you see a few different profiles. The surface brightness profile showing where the clump is becoming bright. The extinction profile does show gradients, but there's no general trend. There's no property that all the clumps do. But the right shows age. And what you see is that almost all clumps, what they have is a very young center and then an older outer part. Now, this is consistent with a picture that was actually put forward in theory by Frederic Bernoulli and others, where you have this old casing of the clumps, and the clump keeps accreting new gas onto it. That new gas finds the center of the clump, it makes new stars, and those young stars dominate the light. It becomes very challenging to measure the total light of the clump, the total age of the clump. But Laura showed that with dynamo galaxies, you can break these things up, and you can confirm this picture quite well. So what we have is a large number, basically all of our results on dynamo clumps are pointing towards long-lived scenarios. So what does that mean for bulge formation? And what it means is that clumps are making it to the center of the galaxies, but are they really adding much mass to the clump, to the bulge, remains mixed, and that basically depends. So on some of the dynamo galaxies, what I'm showing is we can measure the total mass in clumps and divide that by the total mass of the galaxy. And then that's their sort of estimate for how much the bulge mass would get. We get everything from 5% to over 50%, which means there's a range of properties of bulges that would be made out of a range of different clumpy galaxies. I'm totally okay with that. there's a whole bunch of different types of bulges in the local universe. And so I think it makes sense that there's a bunch of different starting points. Also, another thing that's completely missing from this picture is what happens at the intermediate redshift range between 0 and 1. I think there's some interesting stuff that's happening with studying accretion histories in edge-on galaxies that I would like to see more of that can kind of complete that picture. But I think getting a mix is definitely okay by me, given that there's a mix of bulges in the local universe. So I think in the end we can say that the evidence we're getting from DYNAMO galaxies is they're definitely adding mass to the bulge. There's still a huge uncertainty, and that's in the gas masses. Definitely these clumps will carry gas mass to the center, but we have no idea how much. We need ALMA observations to do that. Anyway, thanks very much.